So we still have some people coming in. Let's admit them. So this is the GUI, and I will close this. Of course, you can model right from this interface, but actually, I really do not like to go from here. So what I'll do, I'll close this, and then I will create the first node. I've created the first node, and if you're in Staad Pro, one of the things you have to watch is this coordinates, okay? You can see the Y direction going up, the X direction, and the Z direction. You should always look at this point so that you will know exactly where you are going. So I just need to be sure that we are following so far, so that we'll be sure that everyone is following. I would like to know if there are challenges. I'm sending a message to the group chat. I want to be sure that we are all in order. The audio, the video, everything. All right, so I can confirm that we are good. All right, so I've created the first node. Now, this is the basic 3D coordinate that you know. If we are modeling a building, let's say you're using Orion or any software, and you want to model something 3D, it's usually more convenient to start with the plan view, okay? So for me to get to the plan view, I will toggle from this point, say view from Y. That's you are viewing from the positive Y direction, which means that you are viewing from the top of the building, the basic plan view that you know. And if you watch, the coordinates have changed. The Z direction downwards, and then the X direction to my right. Any direction that the arrow is pointing is the positive direction. This is what I mean. I want to create the nodes that will define our column points. So I'll proceed, I'll highlight the node, copy, paste in the S direction. Let me say 5 meters. The second node has been created, which is this. Let's assume I want to create another point or another node or another point. You know, if it is in Orion, it is just like doing the orthogonal axis generator or something like that. So let's assume I have another panel of 4 meters. Let me say copy or paste in the positive X direction, 4 meters. Okay, I have something like this. I want to create the other point. I will copy and I will paste. It will now be in the positive Z direction. Let me say 5 meters, or let me say 6. So we've been able to create something like this. I will keep it simple. Let's just go with this model so that everyone will follow properly. So this is what we have created in 3D. These are our column points, you know, something like this. I want to create the next level, all right? So I will copy and I will paste in the positive Y direction because I want to go up. Let me call this, let me say the story height is 3 meters. As you can see, the second level has been created. And now let me say the roof level is 3 meters also. I can paste again in the Y direction and I will say 6 meters. So I've succeeded in creating all the points that I need. The next thing to do is to create the members, talking about the beams and the columns. Okay, there's a very fast way of doing that. You can do it one by one. You go here, pick the add beam command. You add, yeah, and it continues like that. But you can confirm that if if uh, if you have a very large structure, okay, you may not be able to do this one by one and all that. So the fastest way, you can highlight all these members, okay, and then you go to geometry, connect beams along the y-axis. Then it will tell you the number of members created. Say 12 members created, you say okay. You can see that all the columns have been formed, all right? So I can highlight again. I can change the view, highlight the nodes again, say geometry, connect beams along the x-axis. I'll be sure that the horizontal beams have been created. This is the 3D view. I'll go to geometry again. I'll say connect beams along the z-axis, 6 members created. So with this, we have formed the basic geometry of the structure. All right. So there is nothing more to it. Let's assume there is a cantilever and all that. You can go ahead, maybe copy this guy, paste, and form what you want to form. So, or let me just try it now. I will copy. I'll just highlight these two guys. Remember that this is the x direction. So I'll say copy and paste. I'm going in the x direction. Let's say it is a 1 meter cantilever. Okay, you say 1, and then this nose gets formed. All right, so after creating the geometry, you're sure you've gotten what you're looking for. The next thing that we can do now is to form the floor slab or the meshing. I will also go through a familiar process. I'll highlight the whole of these guys. I will go to view, say view selected objects only. I turn it back to plan view. Now, meshing is an important aspect in Staad Pro because it influences your results. Just as we know, Staad Pro is a finite element based software. So you should know that the finer your meshes, the more accurate your results. But then you should know that the finer your meshes too, the longer it takes to analyze the structure, because it means the computer now has, let's say, a very large matrix to solve, because you know that this is generally all about solving systems of linear simultaneous equations that can get up to 1,000 by 1,000, depending on how large or how complex the structure you're dealing with is. So meshing is important. And Staad Pro is that flexible that it gives you options, okay? You can go for rectangular meshes, you can go for square, you can go for triangular. It all depends on what you're looking for. For instance, if you have an irregular structure or a structure that the form is not regular, yeah, you can't use rectangular meshes there. It has to be triangular and all that. So these are the things you have to watch out for. So I want to create the floor slab using the mesh command. Some people make the mistake of using 4-noded slab. It's a wrong assumption. You are not depicting the exact behavior of the structure. Okay, so it has to be a mesh. So this is the command, generate surface meshing. I will activate it. I will start from here, moving in the anti-clockwise direction. If you go for polygonal meshing, you're going to have a kind of triangular element or something like that. This is what you're gonna have. It will work. There's obviously no problem using this, okay? I'll do Control Z to get it out. But I want to use another approach. I will go exactly through the same way again, but this time around, I'm going for quadrilateral meshing. Okay. Now this is 5, 6, 5, 6, representing the dimensions or the sides of the slab. So I want to adopt a uniform meshing, so that the whole thing will be square. All I just have to do is to multiply by a constant factor. All right. So 5 times 4 is 20. So I will go for 20 divisions here. 6 times 4, I think, is 24. This is 20. This is 24. When you apply, you see that you have a very fine mesh that is uniform. Okay. Now, let me say Control Z. If you decide to do it the other way around or following the default division, the default division is 10, 10, 10 all through, and you apply. You see what you're going to have. And then by the time you try to measure, sorry. So by the time you try to measure the node to node distance, this side, sorry, from here to here is 0.5, and from here to here is 0.6. So it's not square. I will go through the undo process again. So, right. So let me just go with a factor of 3. 5 times 3 is 15. This is 18, 15, and this is 18. You say apply. So you can see we have a bigger mesh, which is still uniform. If you check the distance, this is 0.33. This is 0.33. All right. So I will go over to the next panel. The same anti-clockwise direction. Quadrilateral meshing. The same factor, 4 times 3 is 12. 6 times 2 remains 18. 12 and 18. We say apply. And now so you have a uniform mesh. Okay. Now this is 1 meter. So I will mesh the cantilever portion too. I will go this way, this way, this way, and this way. Quadrilateral meshing. I will say okay. 1 times 3 is 3. 6 times 3 is 18. This is 3. And this is 18. You say apply. So if I view the whole structure, I'm sure I moved something. All right. So if I view the whole structure, this is what we have. So I hope this makes a little sense to us. So I'll be going over to our chat room to see what's happening. Someone is asking why anti-clockwise direction. Well, it's not yet time for questions. I will attend to that later. All right. So having done all this, the next thing is to move on to general. Okay. I will come to general. This is where you can define the properties of the sections you're dealing with. Okay. So I will say define. Here you can see different sections: circle, rectangular, T-beam, trapezoidal, and all the rest of them. So I will go for a rectangular section for our columns. Let's say 230 by 230. I will enter 0.23 by 0.23. I will add. Okay. And now I will say our floor beams are 0.45 by 0.23. So remember, this is YD. YD represents the depth. ZD represents the width. Okay. I'll change this to 0.45. Remember, the material has to be concrete. Okay. I will say add. Now let me say the roof beams are 0.3 by 0.23. I will also add, and I will close. So for me to assign to the columns, I will go to select beams parallel to the y direction. All the columns will be highlighted. Okay. You now say assign to selected beams. It gets assigned. All right. This is for the floor beams. I can change the view. Use my cursor to highlight the whole thing. This is what the 3D is like. All right. I will say assign to selected beams. I will say yes. Now for me to assign this to the roof beams, I can go through the same process again, highlight this, say assign to selected beams, and I assign. Now, for me to define the thickness of the slab, I just have to say thickness. Let's say it's a 150 thick slab. I think we have a slab of 6 meters by 5 meters. So slab of 150 should work. Provided we don't have a very heavy live fluid. So this is 0.15. I'll say add. So I will change notes in Staad Pro. The node you use for beam is not the same node you use for column, and it's not the same node you use for your plates. Okay. So for instance, I want to assign properties to the plates now. I will need to change to plate cursor. Okay. You can also use assign to view. It will work, but it doesn't work in every case. You need to master Staad Pro very well before you can start assign to view. Okay, so I will just change to plate cursor, highlight the entire plate. This is the 3D view. You can see that the plates are highlighted. Assign to selected place, you click on assign, and you say yes. So this is what the rendered 3D view is like. So this is what we have as a 3D view of the structure. All right, this is the cantilever portion. If you look very well, you will see that the slab is at the middle of the beams. Yeah, the answer is yes. Staad Pro connects members at their centroid, okay? So anything Staad Pro is doing is based on center to center dimensions. So this will give you a clear view, okay? You can see that the slab is attached right at the center of the beams, okay? Now, this has no effect whatsoever in your analysis results. Peradventure, you want it to look realistic or for whatsoever reason, all you can do is to use the offset command to drop the beams so that the surface of the beam will flush with the surface of the slab, which we can say is a more realistic situation. But one thing is, when you do this, you are going to have, what will I say, a kind of high axial forces, because I think from what I can understand, Staad Pro treats that kind of thing as a form of imperfection. So we move on. So this is the 3D of what we have. And I hope it's all clear. So the next thing we can do is to define the support conditions of the structure. You just click on support, and then you can come to create. You see different types of support here. Fixed, which is the normal fixed support, you know, pinned, fixed bolt, enforced, and all the rest of them. You can also do foundation when you want to follow elastic approach to analysis of your foundation, be it raft or whatsoever. But here, I'll just keep it simple. I can model a raft directly on this interface. I can do that. I can also use this to model footing. You can put in the length, the width, and all the rest of them. Then you have to put in also the modulus of subgrade reaction. I always talk about this, which you can obtain from what is called plate load test. But you need to correct it for the size of the footing. Okay? So simple, I would like to adopt fixed foundation, fixed support, a theoretical assumption. All right, so I will highlight the entire node at the base and I will say assign, and now this comes up. We have modeled the structure, we have assigned the properties, we've put the support. The next thing to do is to define the loads. You click on load and definition. You come to load case details. You come to load case details. You say add. The first load case is supposed to come up. I will call it dead load. Okay. And now the next load case comes up. I would like to call it imposed load. All right. So we need to define the dead load and the imposed load. If you look, we can tell Staad Pro to calculate the dead load automatically. But first of all, I know that the unit weight of concrete in Staad Pro is not 24, it's 23 point something. So I need to go to Staad Editor to take care of that. So that we'll be sure of the results we are getting. The editor. This one is just like since we started, this is where the coding, just like the coding is being done. Just like the Staad editor. Those that are good can model an entire structure from here, but I think it's gonna be something challenging. I'll change the unit weight of concrete to 24, and then the poison ratio to 0.2. I'll save the changes, and then I will return to the interface. Well, wind load on Staad Pro. Wind load, you have to define, but you should know that based on the version of Staad Pro that I have here, the wind load is based on, I think is ASCE or something. It's not based on BS 6299 or Euro code. Just hold on, I am working from my virtual machine, so it's a little bit slow. So just let's be patient. Wind load, unless you define it manually, which is what I normally do anyway. I will do the wind load analysis manually, obtain the forces, and then apply it to the structure. But that's no big deal. You can model, you can define wind load based on the provisions available in this particular version of Staad Pro. But alternatively, you can do your calculations, then apply wind load as a horizontal action, which you can convert to concentrated loads or uniformly distributed loads, depending on what is good for the structure you are dealing with. But for this structure that is less than 6 meters, I don't deem it important to think about wind load. So that's the case. Sorry for the delay. I'm on my virtual machine. It's very slow here. Okay, we are here now. Back to where we were. So we are sure now that we are dealing with concrete. The unit weight is 24. So I'll go to dead load. I'll say add self weight in the y direction -1. I'll say add. So this calculates the self weight. So self weight of slab, self weight of column, self weight of beams. This takes care of it. All right. So the next thing is member load. This member load, I would like to define the block work here. Let us assume that the unit weight of block is 3.5. And now for a floor height of 3 meters, let's say less the depth of the beam, 300. So let's say 3.5 times 2.75, where 2.75 is the height of the wall. Under assumption, I'm getting a block load of minus 9.625. Remember that it's negative because the load is coming down. All right. Stapro is sign sensitive. If you leave it as positive, it will assume that it is an upward load. Okay. So I'll say 9.625 to be the block work load. All right. I'll say add. Now, we know that when we are designing structures, we normally make allowance. Let's say finishes, partition allowance, and all the rest of them. So that one is a plate load, okay? Like it's on the slab. So I'll go to plate load. I will say in the global y direction. Let me say finishes 1.5. Partition allowance 1 kilonewton per meter square. So I have an additional dead load of minus 2.5 kilonewton per meter square on the slab. Remember that if you put in the local z direction, you will still get an answer that is similar to what we have. All right, so imposed load. Let me just take an imposed load of let's say 2. You say add imposed load. So imposed load of I said 2, right? So plate load global y direction -2. All right. You can make further considerations for the roof and all that. Okay. You can add the roof load, but I'm not gonna go into that right now. So the next thing now is to assign the loads. All right. So for this self weight now, you can say assign to view. All right. So it assigns it to everything that is on your screen at that moment. Or you can change to geometry cursor, highlight the entire structure, and then you assign. Either way you decide to look at it, it will work. So you find out that the self weight has been assigned to the structure. Okay. So I will apply the block workload to the floor beams. All right. So this is it. I'll highlight this. This is the 3D, just in case you want to see it well. I will say assign to selected beams. The block workload has been assigned. Now, the additional floor load, okay, I will change to plate cursor, highlight the entire slab. This is the 3D. Now, I'm assigning 2.5, assign to selected plate, you say assign. This comes up, and now you come to impose load. The impose load is also on the slab. So with the same plate cursor, you can highlight these guys. You say assign to selected plates, assign. This comes up. So we've been able to define our loads. So the next thing now is to define our combinations anyway. You go to load case details, you say add. Instead of this place, you now come to define combinations, okay? So I will call this serviceability limit states. I will say SLOS. I'll bring the whole of this impose load and dead load to the right. For serviceability limit state, the factors are 1.0 GK plus 1.0 QK, something we are familiar with. You say add. Now, I define the ultimate limit state, ULOS, dead load a factor of 1.4, and then impose load a factor of 1.6. I will say add. Now that we are here, no other special consideration to be made. We've defined everything, and we can proceed to analyze the structure. Okay, you can say analysis slash print. You say or add, you close, post print, define commands, analysis results, add, and you close. So we can analyze the structure now to see what is going on. You say run analysis, and then you will ask to watch Structville do its thing. Well, the analysis has been done. I'm getting 2 warnings, which is strange. Let me check what is happening. Members 1 and 3 are between the same joints. Members 4 and 2 are between the same joints. For example, members 1 and 3. So strange warning there. So Okay, this is the post-processing. You can always choose the load case of interest. This right now, this is the ultimate limit state something. You can see the deflated shape of the structure at ultimate limit states. Can see the deflated shape at substability limit states. All right, so having gotten here, you can also look at the support reactions. This is reaction, which you can view. You can view it individually, one by one or something, or you can look at it. You can just look it up here, depending on the load case you want to see the reaction for. Then you can come to the beams, and you can see the bending moment diagram, though this is looking too big here. But with your scale, you can just adjust them to make them look presentable. You can say bending in the Z direction, you can say 50. Yeah, that brings it to the point where we can look at it properly. You can come to graph anyway. Turn off the loads. For instance, if you click on this column, you'll be able to see this is the axial load and the structure. This is the bending moment, and this is the axial force. The same thing here, all the way. You can view the members one by one, all right? So if we come to plates, at ultimate limit state now, depending on the locus you're interested, you can view the bending moment in the S direction. You can view it here. So the maximum sagging moment of the slab is 14.7. The maximum hugging moment is 13.2. So let us assume that you've done your analysis with Staad and you don't want to design with Staad. Or maybe you have an Excel spreadsheet that you need to take your results to. These are the results you can easily pick and do your analysis. Plates also, you can say MY. So this is more like it. So we'll be able to know how to proceed with the design of the structure. So you can view your analysis results and all that for the beams, for the plates, for the columns, and for the rest of them. So having gotten here, the next step now is to go into concrete design, an area which I know a lot of people may not have ventured into. But if you have any questions there, of course, you can ask. You go over to concrete design. Just like another interface within the Structville software, the same job information comes up. You just try to fill engineer, checked, job client, and all the rest of them. And now the next thing is the envelope. You can say new envelope. You can call it E1. Say okay. We are only interested in the combinations for you to use the most critical, all right? So we can go to members, we need to form members, okay? So I can use say members, auto form members. Sorry, this is a mistake. Yeah, it creates sorry, I need to close this. So I'll go back again. Envelopes, new envelope. I'll call this E1. Combinations only. I'll say okay. Now come to members. I need to form the members. So I will need to select the member cursor, okay? I highlight, oh sorry. I'll pick the columns, for them the first members. Let me just keep it limited. Say auto form members. Now, oh, something is happening here. And I'm sure that's why that warning came in the first place, but let's ignore. Let's ignore. It's okay. So for the beams, I can highlight this, the whole of it. I can come here and say members, auto form members. Now, if you change the physical cursor, you'll be able to find out that the beams are now behaving like continuous beams and simply supported beams instead of being broken, you know, into stuff like that. The same thing also can be done for the slabs. You can come to slab. This is the first panel. You can highlight it. Form slab. We form this one. You can highlight the second panel. Form slab. We form this, and then we highlight this also. Yeah. So we've been able to form the members we want to design. You can see slab 1, slab 2, and slab 3. Then you can see the columns, you can see the beams. So note we are neglecting the roof beams and the upper columns, okay? So we go to groups and brief. Brief is just like giving the design information or the data you want to be used in the design. You can go to new brief. I can call this beam brief. Design code is BS8110. You say okay. For the beams, we can accept cover of 30, okay? Now let the concrete grade be 25. Maximum size of aggregate 20, we can accept that. No reinforcement. Let the minimum size of the reinforcement be 16 mm for our beams. Let the maximum be 25. Link size of 8 mm is good. The same thing here. We go for 16 mm bars, 25. Sidebar criteria, minimum spacing, we don't have sidebar. Let the user grade be 460. We go to shear reinforcement. Let's use the center line of support for our design. Shear bar size 8, minimum number of legs is 3, no problem. Let's use user grade of 460. I think we are okay with this. We say okay. We go over to another brief, new brief. We call it the column brief. Okay. We change this to column BS8110. Just in case you want another code, this is hero code 2. I think there are a few other codes here, ACI and all the rest of them. But let's go with BS8110, the one that we are more familiar with. Columns. Let the concrete grade remain 25. Let the steel grade be 460. Aggregate size 20, concrete cover 30. Let the lengths be 462. Let the minimum size, okay, let's just say 16, even though I know 12 will kind of be more economical, but column factors, let's assume the braced columns. Number load cases, we say okay. So new brief also, we'll go for slab. We'll say slab brief. Let the cover be 25, top and bottom. Let the concrete grade be 25. For the beam reinforcement, fees, there are two considerations, fees bar size and fees bar spacing. Let's go for fees bar size. For this slab, let's use 10 members in all directions, or let's use 12 to avoid people asking too much questions. Let's use 12. So if you use fee spacing, it means that you want the whole spacing to be 150 or something like that. Now, Staad will use his hand, to pick the bar size that will satisfy the requirement. But this is just like a limitation on the capacity of the software anyway. So, but I prefer the fixed bar size option. Okay, and now let the steel grade be 460, please. Wood and armor, yes, let's consider that. General, we say okay. I don't think we have any other thing. Now the next thing is to define the groups. I will change to this view. Highlight all the beams. I will go to new design group. Design group 1. Let me call it beam group. Now the associated brief is this. You say okay. Now another one is the columns. I'll highlight the whole of this. This is the 3D view. I will say new group. Of course, column. Then I will call it column group. You say okay. Now I will go to slab. Just say for slab 1. This is slab 1. This is slab 2, and this is slab 3. You can say okay. Sorry. Slab design 1. You can say okay. New slab design. You can say slab design 2. You say okay. New slab design. You can say for slab design 3. You say okay. So now that we have assigned everything we need, the next thing is to um, the next thing is to uh, go over to concrete member, which is just like the design. You see everything fail. That's just because we've not done the design. All right. So we go to design now. You say okay. So as you can see, all the beams have satisfied the hugging, the shear bar, the span depth ratio, and all the rest of them. I'll quickly run through some of the results that can be of interest to you. The main layout. You can also check out what the guy is providing. 26.4, and now the rest of them. This is the bending moment diagram. So it's designing for a moment of 76.6 and all that. Diameter of bar 16. Okay. Now this is a typical detailing, if I may say. And even if you are to export this drawing, this is the detailing you're gonna see. And that's why I say that detailing from Staad is not too fantastic, but it's something that you can make do with. So this is just the layout, okay? As you can see here. You now come to main reinforcement. As expected, it's providing two number of 16 mm, top and bottom, I think. I'm not expecting any less. 2T16 top, 2T16 bottom. So this is the shear layout, showing the shear reinforcement. So it's providing 8 mm at 300 center to center, which is what we expect. So this is just the shear reinforcement and all that. But then Staad has a nice looking calculation sheet, which I would like to show us. You go to report setup and move all these guys to the back. I just want to go for design detail. I will say okay. You go to print preview. This comes up. I hope you can see the screen. This is member 8, span 1. You can see at the start of the member, okay, the bending moment there, I think this should be kind of hugging. The fixed moment 26.35. Then these are the design steps and all that. So the area of steel required is 171. Now the area of steel being provided is 2T16. You can go to the next page. Now these are trying to check the detailing requirements and all that, okay? So the moment capacity of the section at that point is 59.98 compared to 28 point something, which is the design moment obtained from analysis. So you can see at sagging, which is where I expect us to have the maximum span moment, 55.35. You can see the calculation procedure. So area required 368 is providing 402, which we can accept. This for the next span, I think. So this for the top bar, okay? 76.59 is the design moment. I think we come across that moment. So the area of steel required is 527. So it is providing 3Y16, 3T16 at the top, which looks okay. So it will go ahead and check the deflection using the procedure that we are very familiar with. And of course, also taking into account compression reinforcement if possible. So the allowable span to depth ratio is 33.28, while the actual is 12.38. So you look at it and you say it's okay. So you can go through the entire results one by one. So we can also design for the columns. You say design now. The whole thing is also looking okay. You can look at the layouts. The design moment 20.7, 8.35, and all that. So looks okay. You can also go through the same process of setting up the reports. Bring this back, design detail. You say okay. You can see the design moments, the Azure first, and then I think this looks like a biaxially loaded column. You know, internal forces and all that. The design sheets are there for you to see. So the area of steel being provided is 4x16. Then it will check for the detailing requirements and also design for shear. So it's providing for the links 8 mm, okay, at 125 mm spacing. So that's for the columns. You can go through one by one. So you can go to concrete slab. You know, normally slab in Structville is usually not so cool. I don't like designing slab using Structville and all that, but for this particular event, we can take a look. You can go through the design. So you can see in some regions, depending on the design moment that is designing for another, you can see the design moment and then the spacing. In some areas 150, in some areas 300, in some areas 175. You can that's the way it's done. The displacements, the moments, the regions. I didn't define the region. It is something that is usually done. So this drawing now, export to DSF. That's the way you can move some of your designs and drawings to AutoCAD. But there's a way you shade this. You can check the spacing. You can check the design moments. Okay. You can check the area of stay required. Then you can check the spacing required, which is the one that is showed by default. You can check also in the Y direction. You can check top, you can check bottom. So through this, you'll be able to, put the whole thing together to make sense. All right. So if we should go back to concrete member drawing, you can export your drawings to DSF. That's to AutoCAD format. But just like I said earlier, the drawings are not usually so interesting. So you can take your results, analysis, and everything to another software, but be rest assured that you can rely on the results that have been produced by this software. You can export them and actually use them somewhere else for your design. So perhaps if we meet again, we can go a little bit into other forms of analysis, such as maybe bus covers, raft foundation, and all that. But for now, I'm going to take some questions. I've already seen some questions coming in the group, but for now, I want to take some questions so that we can round up and face other things for the rest of the evening. So thank you so much for coming around. Thank you for listening. Let's look at the questions. If you have any question, you send it across in the group chat. So let's attend to the questions. So let me start. Okay, what of notional load as stipulated by BS code? Well, the notional load stipulated is usually a kind of function of the gravity loads you're applying. It's just based on, in Edo code, we call it the equivalent horizontal load, or trying to incorporate the effects of imperfection in the structure. Yeah, you can go through the process of modeling the loads, or you can as well say a load of 1 kilonewton, you place it at the top just to model the effects of imperfection. But then the truth of the matter is that for a building of this nature, if you put those notional loads and all that, it can influence design of columns, yeah. But at the end, you find out that the computational effort and all that may not really be worth it. So that's my response to that. You can include it. But for a simple structure like this, you can go ahead, do your modeling in a very simple way without compromising on the integrity of the structure. So another question from the 3D modeling, what can best describe the connection of the members at the node? They are all rigid connections. All the members are rigidly connected, which means that they can resist moments, okay? All the members are rigid. They are all rigid connections. Okay, another question, why assuming braced structure when bracing elements are not present? Well, I deem the idea of bracing and no bracing not to be critical in this kind of structure. This is just one suspended floor. No wind load analysis has been done. And the only thing bracing can do is based on how you define the slenderness ratio and all that. But if you look at this frame, I didn't apply any wind load, and if you still want to make the structure unbraced or the columns unbraced, no problem. But then I don't think it will make any difference to your analysis result. But then there are some structures you look at, you don't make such assumption. Two things are involved, because bracing of a structure is more about lateral load resistance, okay? You're talking about wind load, you're talking about earthquake, and all the rest of them. So if you have stabilizing components such as shear walls, core walls, and all the rest of them, yeah, you can say, okay, you have stabilizing components or bracing elements, which means that you are not using your columns to resist lateral actions. Yeah, so in that case, you can say the columns are braced. But in a situation whereby you are using your columns to resist lateral actions, you can say, okay, the columns are unbraced, which is the ideal scenario that we have here. The columns are unbraced, but still, when you look at it, there is no wind load, there is no horizontal action assumed. It doesn't make any difference whether you assume braced or unbraced. So someone is saying, some of us joined late. Can we have the video file sent to us? Yes, okay. So how do we extract reaction load table from report for each footing node? Okay, you can easily get the support reactions. You go back to post-processing reactions. Right here, you can see the support reactions. Okay, this one we are seeing is for ultimate limit state. All right, yeah, this is 197, 197. This is 339, 346, 204, 185. Something is happening somewhere, but we'll just let it slide. Now, you can also come here to this table and go to the summary. You'll be able to see the summary of all the support reactions, all the nodes, and all the rest of them. You can see the summary of the stuffs that we are dealing with here. So, questions and answer time. Is anywhere, yeah. Basically, I just take this lecture as a kind of exposition on the things you can do with Structville, and not as a serious or critical design something, just like a sample model. So everything that we have done here is just basically within the assumptions that we have made. So are there more questions before we go? You can put in your question on the Zoom group chat. You can put your question on the group chat. Okay, how can you set your Staad environment to merge with Orion environment so that results can be compared? Okay, it's a matter of making the same set of assumptions. All right. I've done that in the past. In one of my publications, I was able to compare results between Orion and Structville. You know that Orion will define your loads for you. Basically, you don't apply loads manually the way you do in Structville. In Structville, you define your loads, you assign values, and all that. Now, you need to make sure that you are operating under the same set of assumptions. Yeah, because in Orion, for instance, you should know the assumptions, okay? Support conditions and all the rest of them. Now, you can't, I don't think there's any option of merging the two technically, or just like moving results from Staad to Orion and all that. I don't think it's possible. But all you just have to do is make sure that the assumptions are the same. the unit weight of the concrete, the support conditions, the material properties are all the same. So by the time you do all that and then carefully model, you find out that you should be able to compare the results that are coming from this. And now note that Orion by default includes the effect of notional loads, which someone raised in this platform. Orion includes notional loads. In fact, if you go through Orion results, you find out that there are about 10 combinations, especially when it comes to the design of columns. About 10 different combinations will be tried, and then the most critical will be used for design. But if you must do that in StartPro, then know that you have to define all the 10 combinations by yourself. So you just have to be careful, know how to, take care of things on your own. So somebody is asking, why did you create the floor mesh in anti-clockwise direction? It was done in anti-clockwise direction to make the analysis time faster. Okay, it's finite element analysis. If you go in clockwise direction, no problem. But there are some cases whereby you may want to go in anyhow direction, and the StartPro will say no. Because this thing, just like if you have done finite element analysis manually, at each node, you assign a number. Number 1, number 2, number 3, number 4, number 5, and all the rest of them. Now, when you start doing your analysis or when you start solving the matrices involved, you find out that you need to start to, how will I put it, carefully, you need to arrange, the nodes serially, like 1, 2, so that let's say if you're solving for deflections, deflection at node 1, deflection at node 2, deflection at node 3, you need to carefully arrange it. Now, that is something that Staad does also. The more time it takes for Staad to arrange the nodes, numbers, and solve and all the rest of them, assembling the stiffness matrix and all the rest of them, it takes time. So experts have recommended that if you should go in anti-clockwise direction, it saves time in analysis. It's just something that has to do with finite element analysis. It's not, if you go in clockwise direction, you still get results, but the analysis results may have may take more time. So does MX in Staad also means MX in Orion? Probably yes, probably yes. But all you just have to do is to, like I said earlier, watch out for the coordinates. Watch out for the X direction. Watch out for the Z direction and all the rest of them. Do you manually draft your drawing, or is it we export the result to another drafting tool? And just like I showed us earlier, the potentials of this version of StartPro, this older version of StartPro to give you drawings is a bit weak. Okay, so if you are designing with StartPro, get ready to do some serious drawing. Just have to. Yeah, or otherwise you can, if you have another drafting software, you can just transfer your data, find a way, take your data to that particular place and then come up with your drawings. Can we have a tutorial in future on advancing this model with foundation parts, raft embedded? Yeah, it's possible. It's possible. It's very possible. Okay. Is there any more questions? So I'm going to call it a day. Thank you so much for coming around, and let's hope that this basic analysis will give you the edge you need to start using StartPro efficiently. So thank you so much for coming around, and do have a good night rest. So I will try my best to make the video available. All right, good night. I'm ending the session.